It is Monday.
Apparently a slow Monday too.
Yeah, we're 6 strong, counting the teacher. Eight's early, but not for you 5. What am I doing? Let's see. Let's share screen. All right, I want to quickly put to rest the project so that you have a sense of whether you got it right. I will grade those later today, I assume, since you turned them in to me yesterday.
That's great, because that project was brutal.
Did it hurt your person?
Yes.
Okay, so let's talk about that. And I'd like you to, interrupt as usual, because my goal, as I said, my goal is to teach you something with these projects. And I, a number of you checked in with me over the weekend, texted back about whether you were right, and that I certainly want to leave you understanding it, and because it just helps you grow in your calculus knowledge. So let's take a quick look at Project Hoots. So let's see, I'm going to start quickly from scratch. I'm going to shoot a shot from 8 feet high, and I'm going to shoot let's do something stupid. Let's shoot a 28-foot shot. So there's my parabola. That's the only 2 things I know about my parabola. And as you know, there's like a low parabola shot. Maybe you did the project enough that you understand that's not going in. And then there's kind of a high shot. And so the other thing that we understood was the fact that the next thing that you actually have is an angle. So that's all you had. And we talked about this, but me introducing it and you getting into the problem enough to actually understand it are sort of 2 different things. So I'm going to shoot a 62-degree angle for no good reason. And so then if my shot goes in, which remember assumes that you actually throw it at the right pressure, because you could do all of that and it could land, clear across the gym, or, go boo and land right in front of you if you didn't shoot hard enough. So we're actually way oversimplifying this, but that's all that I know. And my first job was to find the equation, the parabolic equation of the form ax squared plus bx plus c. And as I've said before, my goal in all of these kinds of things is to get you to learn to speak the language of math. And yeah, that is painful. And I somewhat apologetically give you these projects because I certainly don't want you to overly suffer. But as long as you leave them kind of going, yeah, that makes sense now. I think we've learned something, and that's important. So number 1, and I shared much of this with you, but number 1, that means the point y of 0 better be 8. Well, that's really easy, because if I put 0 in for x, I end up with c equals 8. So there, cool. I already know one thing. 0, 8 has to work. And then I also know 2810 has to work, but we'll get to that in a minute. The other thing I know that thanks to calculus is the 62-degree angle. So what about the 62-degree angle? And remember, that's only the angle at the start. 1 second later, it's now lower than that. Remember, angles are always measured from what we call 0, which is 3 o'clock on a clock in trigonometry. And so what is that? Well, since the tangent of an angle, and I told you this, tangent of an angle is opposite over adjacent, since in a right triangle, if that's your angle, opposite over adjacent, hey, that's the same as rise over run. That's the same as slope. So the tangent of 62, I'm going to just round this off so that I'm leaving this as straightforward as possible for you. If I say, what's the tangent of 62? My calculator says 1.88. Well, that's actually the slope at x equals 0. In other words, only at the start. That's the slope right now. That's the slope of the tangent curve. That's the slope right at that point right there. And notice that looks about right. Doesn't that look steep? I mean, that's roughly a slope of 2, a rise of 2, and a run of 1. Like that's the angle we're defining right there. So that doesn't that look like it would be about 62 degrees? So that's kind of cool. That makes sense. But as I've told you before, like I got an A in calculus, but I couldn't think like this. So you should not feel like you're doing something wrong if you find this difficult. Well, that's cool. What good is that? Well, don't I know if the equation is y equals ax squared plus bx plus c, that y prime would be equal to 2ax plus b, because the derivative of x is 1. Remember, a, b, and c are constants. We just don't know what they are yet. So that's why the derivative of ax squared is not product rule or something like that. Derivative of x squared is 2x. Well, that means I know that that whole thing is equal to 1.88. Well, and remember, that was only true at x equals 0. So that's really exciting, because that means I can go back here and put x as 0 in, which means b is tangent of theta, or 1.88 approximately. So actually I know b and I know c for my parabola. And lastly, if I take the equation, excuse me, and I plug in the point x is 28, y is 10, I'm supposed to get y is 10 when x equals 28. So that'd be a times 28 squared plus b, which I just figured out is 1.88 times 28, plus c, which is 8. In other words, that's an equation with only one unknown in it. And so I can solve for a now. So I need to take 10, subtract 8 from both sides. So I get 2 over there. And then I'm going to subtract this 1.88 times 28. Whoa, 1.88 times 28. And then I'm going to divide by 28 squared, divided by 28 squared. I got a is approximately negative 0.0646. What about that am I not surprised about, you algebra studs? Why am I not surprised? What about that a am I not surprised about? I know it's early.
That it's negative?
And it was.
Yeah, it's negative. What about the size of it? Why is there no way it was like -3?
Well, wouldn't that make the parabola much larger? Like the angle?
Yeah, remember if a parabola is really steep like this, that's what you get for a large a value. In other words, you have a steep slope, whereas our shot was kind of, long. And so I'm going to get kind of a parabola that's, nice and wide, kind of open like this, as opposed to steep. Remember, maybe these are things you still know from Math 111. If not, learn them more deeply. So this is amazing, because now I can say I actually have the model. And by the way, one little sort of warning about this is that a value is so small that you can't afford just to round it off to like 0.06. It might be surprising how much it misses the rim by if you shot it. If you rounded it that much, it's a really tiny number. So all those extra decimal places, maybe I didn't even carry it far enough. But I now have the equation, the actual equation for that curve. And so I could graph it, and I should see it flying through the air on my graph paper and actually hitting the point 2810, or at least real close based on rounding. So cool, this thing is flying through the air. Now, were you able, between questions you asked me and your own thinking, to understand the difficulty of this statement? If I'm throwing a piece of paper and I'm trying to hit something or throw it in a garbage can or something like that, there's two shots that are the same exact shot. One of them is a small garbage can that's really close. Another one is a large garbage can, but it's really far away. Can you see that those can be the same exact shot? It really comes down to not how much air do you have, how much room for air do you have in inches. It has to do with how many degrees of freedom. In other words, you're going to try to shoot this ball at 62 degrees and you're not going to be able to do that. So the question is, how much can you be off? Well, you can't just say 2 inches, because if that hoop is right in front of you, 2 inches is unmissable. You could never miss when it was that close. But if it was across the street, you're probably never going to make it. So just 2 inches is not enough. So in the end, it's how long is the shot? And we now have the ability to find the length of the shot. Which is arc length, AKA length of the shot. And again, you would all agree with that. It's like, if I said, hey, you want to bet me 10 bucks I can make this shot, you would analyze, you would just look at it and say, well, how far is it? And if I was, holding the cup right in front of me and dunking it into it, you're like, I'm not going to bet on that. You're not going to miss. That's like 1 inch away. But if it was 50 feet away, then you're like, okay, yeah, I'll bet you 50 bucks, man. You're never going to make that. So does it seem logical as to why we would be trying to figure out the length of the shot? Well, you understand how to do that. The arc length, and the project came right behind this discussion for that exact reason. The arc length is the integral of, was it 1 plus the derivative squared? Well, what's the derivative? The derivative of, I'll go ahead and write it. Now I'll just do it. The derivative of y, we have this equation, but we need its slope. If I take the derivative of negative 0.0646 squared, then I'm multiplying that 2 by this, which makes it about 0.1292. Negative 0.1292x. And then the derivative of 1.88x would be 1.88. And that is squared dx. That's the formula for arc length. 1 plus the derivative squared, square rooted. And then I evaluate it for, well, where is this ball flying? Well, notice I'm working with x's, and doesn't my ball fly from x is 0 to x is 28? So in my case, that's from 28 to 0. Is that a takeable integral? Because that's something you will be able to do yourself. The answer is no, although I don't think that's necessarily obvious, at least not right now. So I am cheating. As I warned you kind of about arc length, because you're taking a derivative and squaring it and adding it to 1 and putting it under a square root, even the simplest of equations are going to get really messy as a result of that. So that's kind of terrifying. So I'm just typing in exactly what I see written right there. Negative 0.1292 x plus 1.88 close parentheses, square it. Got to make my window bigger because my usual window doesn't go out to 28. So I'm taking my x max out to 30. I don't really care what the graph looks like. But the TI says that the arc length, let's see, can't see a graph. Second, calculate what is the area under that curve from 0 to 28. And I'm getting a ludicrous graph because my screen was set weird, but I don't care. The answer I got was 39.455 feet. Just a quick calculation. Let's see. I'm going to erase this, but
I have a quick question.
please.
So your 28 there, is that the edge of the rim or is that the middle of the rim?
Center. We're
Center,
shooting-
okay.
Yeah. So just a quick calculation. If I threw the ball straight at the rim, that would be a horizontal throw of 28, vertical of 10. So if I do Pythagorean theorem on the square root of 28 squared plus 10 squared, if I do that, I get 29.7. So I would expect my answer to be more than that because I threw it up in the air in a curve. In a sense, the hypotenuse of my right triangle is this, dotted curve up here. And of course, it would help to have an actual Desmos drawing of it so that I could, even see how curved it was. So the fact that I'm, a lot larger than 29.7, at least that looks reasonable. It's about the only thing I can do to kind of check it. So, okay, I'm happy with that. So of course, are you going to make the shot? Well, it depends how far away it is. That's kind of a duh, right? And what's cool about this is the ball is actually flying on a curve. You can't measure the distance just as 28 feet because 28 feet is part of the shot, but it's like, well, it depends what angle you shoot at. If you shoot at too steep of an angle, then the ball's got to fly really far, and that's a terrible shot. You're never going to make that because you're sort of throwing the ball a lot further than you need to throw it. Cool. Now, what about error? And here is what I left you with last time. How much room for error do you have? So what I left you with in class was this. We have the rim sitting right here. That's kind of the front and the back of the rim. And the ball is traveling down through this center point, kind of like this. And I helped you understand what was not obvious by any stretch and which was not obvious to me when I, if you will, made this problem up. Wow, my circle was so bad that it didn't even draw a circle when I tried to draw a circle. That's terrible. So what we talked about was the fact that when the ball is right here, where's here? Well, here is perpendicular. When the ball is perpendicular to something, that's when you're the closest you're ever going to be. This right here, that little chunk, right there is the air. Again, I left you with that, but whether you're in a spot to understand that when I was explaining it, I'm not sure. Now, what we talked about is the steeper you shoot the ball, if you shoot it at 70 or 80 degrees, you're going to get a nice, big, large air. The ball is going to have a really good look at the rim. If you shoot really flat, that air is going to be really low. But if you shoot really flat, then your arc length isn't quite so long. And that's why this is such a cool problem, or such an engaging problem. So what I explained in class was, well, fortunately, that creates a approximation of a right triangle. The reason I say approximation is because this purple line right here isn't really a line. That purple line is curved, but in that short of a distance, like a couple of inches, it's basically straight. And we talked about the fact that since the rim size was given, if I remember right, that was 18 inches, then that means I know that that is 9. I know the hypotenuse of that right triangle is 9. What else do I know? Well, remember that y prime, which we said a second ago, was negative 0.1292x plus 1.88. Again, I think people leave calculus being able to take a derivative, but don't understand what they actually just did. Do you remember, as I've said a lot of time, this is a slope finder. I like to think of it that way. It's like an equation that finds the slope, any point you want to be at. Well, if I found the slope where the ball went through the rim, notice I don't exactly know where I am right here. Does it make sense? Right here at this point, x is 28, and now I'm past that a little bit, like maybe x is 28.1 or something like that. But if I move the ball back up here, not very far back to 28, then I can actually know what the slope is right there. So if I stick negative 0.1292 times 28 plus 1.88 into my calculator, I get negative 1.8176. Again, I'm curious to know, do you understand what you just found? What is that? What does that have to do with this picture I just drew? Somebody tell us.
That's the slope of the ball at that point, at 28, like the slope of the parabola.
That's exactly right. That's the slope of the curve. So what I'm saying is, well, no wonder it's negative. Isn't the slope of that line negative? And isn't it pretty steep, like -2 for a slope? It's not the same as it was. Remember when it took off, it was 1.88. This is a little bit lower than that. You might even not be surprised by that, because if it took off back here at 0.8 and it was 1.88, then it's going to be 1.88 again when it's level with that. But if it's up here, it's not going to be quite as steep. So the fact that that's a little less steep actually makes all kinds of sense. So I think I didn't screw that up. But again, what's cool about the slope? Well, the slope is identical to the angle. So if I took the inverse tangent of that slope, in my calculator, I'm just saying second tangent of the answer, I get negative 61 point, I'll call it 18 degrees. I just converted that to an angle. Well, remember that in trig, measured from 0 to the curve itself, that's what that angle references. And notice it says negative. So I'm being told, if you will, that this angle right here is 61. I'm going to write 61.1 just so it doesn't, what did I say it was? 61.18, was it? No, 61.2 then. I'm effectively having a really good approximation for what that angle is right there. Well, if that's true, then don't I know everything I need to know about that right triangle to figure something out? And again, it's calculus. When I invented this problem, just because I'm a curious human being, AKA nerdy, I didn't know this was a calculus problem. I just wanted to figure out, like, why does somebody who shoots a basket really low never make it? And why, when I try to shoot, I played a lot of basketball as a kid, why, when I try to shoot a ball really high, does it never go in? Like, why is that? It's just, I don't know, or is there some best angle? Because clearly if you shoot too low, you never make it. If you shoot too high, you never make it. So the obvious answer is there must be some place in the middle. I wonder if there's like a best angle you can shoot at. That was my initial question. I can't remember where that came from. Could have came from boredom. I don't know. And this sort of drew in, and one of the reasons it's one of the favorite problems I've ever made up is it drew in like all the math I'd ever learned. Like there's a ton of algebra in this that you got to be good at, and there's a ton of calculus. Calculus keeps showing up. I couldn't answer what I thought was a fairly simple question. I couldn't answer it without calculus. It was amazing. So if I wanted to know now that I sort of own the right triangle temporarily, if I call this length L over here, maybe you can see why I'm after that. And then I could say the sine of 61.18 degrees is equal to opposite, which is L, over hypotenuse, which is 9. So now that I own the right triangle, I can figure out what that length is. So if I take 9 times the sine of 61.18, I get 7.885. L is approximately 7.885. By the way, what are the units of that? I was thinking all my units were in feet, but remember that 9 up there was 9 inches. Like that was the size of the rim. I was thinking of that as 9 inches. And so this length is actually 7.885 inches. Do you see now that I can figure out what that error is? So isn't the error that whole distance, 7.885, minus the radius of the ball? So that green radius of the ball there, I forgot, was the ball 9.5? The ball was 9.5. So the radius was 4.75. Better double check that. I don't want to get it wrong. Yeah. So if I take that number minus 4.75, I actually have the error, which in my case is 3.135. So my error is 3.135. And I'm going to make sure to note that's in inches. So the two things you got to know is how far is your shot and how much room for error do you have? Well, I now know both of those things. I know the length of my shot, 39 feet, and I know how much room there is for error. Notice I have a 3-inch error as the ball slides through the rim. And again, I'm simplifying this by making the ball a swish, if you will. It's not that you couldn't hit the back of the rim and it would still go down. The error is actually a hair larger than this, if it makes sense. But this is, in a sense, the guaranteed. It swished. It didn't hit the rim at all. And so we're ready for the final step. So I conceptualized this on my paper, the angle of error by kind of drawing a right triangle where this was the arc length and this was the error. And this phi angle was effectively the degrees of freedom. How many degrees can you be off? And I guess I'm interested to understand why that's important. It doesn't matter if you're 3 inches off. That alone doesn't tell you anything. You also have to know how long the shot is. If I put those two together into an angle and change it to degrees, then now it doesn't make any difference what the shot is. Like, is it close or is it far? I've turned it into a degree. And I'm expecting something like maybe 2 degrees or something like that, maybe for an answer. Well, you understand that. If I take the tangent of phi, that would have to be equal to, since this is a right triangle, the opposite, the error, over the adjacent, which is arc length, 39.455. What's wrong with what I'm writing here?
One's in feet and one's in inches.
Yeah, if you do it like this, then you're saying you have a 3-foot error, which means you're going to have a pretty good sized angle, but that's not, one of those is in feet. So I'm going to add to this down here times 12 and make them both into inches. So if I say 3.135, actually, I'll write that out, 39.455 times 12. So I'm actually taking the inverse tangent of 3.135 divided by 473.46. Second tangent, 3.135 divided by 473.46. I get 0.38. Wow, that's incredible. Do you understand what that means? That means if you shoot, and in my case, remember I shot a 28 footer, which is like 5 feet longer than the NBA 3-point line. So this is a sort of a ridiculously far shot. But basically to make that shot, I'm going to choose my angle. If I happen to choose a 62-degree angle as the angle I'm going to let go at it at, then I can't fail that by more than 1/3 of a degree. I can go 1/3 of a degree above it or 1/3 of a degree below it. If I can't do that, I'm not making it. And added to that, I even have to push it with the right speed.
So if the closer the shot would be, would that essentially make that angle larger, depending on
Yep.
depending on the angle you shot?
Yep. If you get closer, then it's not near as, kind of unlikely to miss. And so, yeah, this is very much worst case scenario, which I wasn't really planning. Now, let me just play with something really quick to show you something kind of interesting as a takeaway from this. And again, I know it's early in the morning, but like interrupt, is that Is that meeting with your logic? So let's see, I shot 8. Let's just check my work. So to grade yours, this is what I'm going to do. I'm going to go in and I'm going to type the initial height that you told me. I hope you told me that because I can't know it if you didn't tell me. And it's a 30-foot shot. And then you tell me what angle you chose to shoot at. And I made a Desmos. And this is the other thing the reason I'm showing you this is because this is what math looks like in the real world. I mean, if it's actually hard as this problem is, then people try to automate it. And so one nerd has made an app that does everything, in our culture. And so, we aren't needing to do this kind of stuff if it's actually really hard. So let's see, let's fly out here to 30 feet. So here's the ball going through the rim, and notice that's a pretty big angle that I shot at. Oops, I screwed that up. That's a pretty big angle that I shot at. And so the ball seems to have quite a bit of room, quite a bit of freedom, right? But my shot is really long. That's a really high shot. People don't shoot. It doesn't look like they shoot that high, you might say. But what I'd like to show you here that's really cool is I've already calced all this stuff. Oh, it was a 28-foot shot. Sorry, it wasn't a 30-foot shot. I was like, I got my problem wrong. Notice I have the air 3.05. I forgot what I got, but it was about that. 3.135. Because I used an equation to do this, nothing is rounded. So that's why this answer is a little more accurate. I got 3.13 a minute ago, and this is 3.05. That's a little more accurate. And then there's my arc length, 39.46, and I had 39.455. And then this actually calculates, notice the inverse tangent of the air divided by 12 times A, that's 0.369. That's the answer that I got just a minute ago. So that's what I'm going to do to grade this. But what I'd like you to watch really quick, just because now we can actually analyze this. In one respect, we're done, and that's really cool. But in another respect, the real question here is not pick some random shot and shoot it and see how much error there is. The bigger question is, what's the best angle to shoot at? Would you agree the best angle to shoot at is the one that makes that angle the biggest you could possibly get it? Do you understand that? I want the most degrees of freedom. Like if I could change the angle, well, let's go change the angle. So it's 0.369. Let's see, can I see both of those? Yes, I can see both of those at the same time. So let's change it to 60. Let's change it to 60. So right now it's 0.369. Do you see how it went to 0.360? So that got worse. Do you agree with that? 62 is a better shot because it's 0.369. What if I go to 64? 0.373, that's even better. 373. So it's 373. What if I go to 65? 3733. So we're pretty much there. 3733. What about 66? So it's 3733. Now it's 3723. So 65 was a little better. And now I could go further and be like 65.2 degrees or something like that. But what this is telling us is that if you shot a 65-degree angle from 28 feet, that'd be your best answer. So what I'm curious about just really quick, and I actually don't know the answer to this, is let's back it up to a free throw. So do you notice what Justin said earlier? Look at the air down there. The air went up to 6.8, which is double. It was 3.7 and now it's like double. You have twice as much air. But even then, it's still less than 1 degree. I mean, isn't that amazing? But I wonder, is it still 65? Is that the best angle to shoot, or does the angle change with the distance that you shoot it at? So I'm going to take it down. So right now it says 6.835. I took it down to 64 and it got worse, 6.797. What if I go back to 65? So it's 6.835. What if I go to 66? 6.845. I'm sorry, 6.848. If I go to 67, 6.834. So there it's actually 66. So it is a little different, but not very much. So it turns out there's a best angle to shoot a basketball at, and it's right around 65, 66, kind of no matter where you're at. Now maybe if you're shooting super close to the rim, like we had a 3-footer or something, just right into the rim, maybe it would change in a more radical way. But kind of the average shot, kind of out there from 3-pointer to 15 feet, you should be shooting like 65, 66 degrees. And what's interesting is even if you get online and just find some NBA stud, like the best NBA shooter in basketball, and you kind of freeze frame their shot in some video you're watching and just stick a protractor on the screen, they're not the best by accident. They'll be shooting really close to 65 or 66 degrees. As I told you before, I doubt it's because they did a bunch of calculus and some nerd, taught them how to play the game. I bet they just made it to the NBA because they accidentally were shooting at the right angle. Does that make sense? So I'm kind of curious about that. I'm curious if anybody actually uses this as an instruction for somebody. Let's say you move into college, like, you're good enough to have eye-hand coordination, so you're pretty decent in high school. But then when you move to college, somebody films you shooting and, sees that you're shooting at, say, 60 degrees or something like that, and you're still good, but to tell them, hey, you should be shooting a little higher of an angle. I wonder if that could actually, I wonder if that's significant. I mean, is it going from 60 to 65? Is that going to actually change their shot percentage, their make percentage? I mean, would that actually make a difference? I don't know.
Speaking as someone who shot beams in high school, I got told a lot to up my angle, but they never gave me a specific angle.
Interesting. Yeah, because you were shooting too flat, so they just told you that.
Yeah, and I think it's pretty well known that the higher the shot is, like, the better shot it is, but they only bring it up when you're shooting like me, where it's like obviously too flat, or if somebody's shooting way too high, they tell them that they're wasting a lot of energy and that's why they're getting tired in the game and stuff like that.
Yeah, and you're not able to be calm because you want your shot to be nice and smooth. If you have to throw it with all of your body weight to get it, clear up to the ceiling, it's kind of obvious when it's too flat, obvious when it's too low. Again, being a nerd, I just made this question up. I have no idea if anybody has ever investigated this in any kind of a way. But the thing I want you to understand is, like, the takeaway from this, you don't have to know any math. I mean, if you now said, hey, 65, 66 degrees, that's the right angle to be shooting at. Like, we don't need calculus ever again. Does that make sense? You can just turn the basketball team loose on that answer. Like, that's where calculus shows up in the world. It does an amazing job, and then makes an algebra equation or something of that nature, and then you just kind of don't need it anymore. But it does something amazing so in one sense, as I've said before, it's everywhere, and in another sense, it's nowhere. But I hope you leave understanding that. I mean, I don't mean, oh yeah, I got it, I can go sign on with an NBA team now, but
Honestly, it makes the shooting baskets a little bit more impressive, considering it's like only close to like 0.7 of a degree, 0.6 of a degree of error. And if somebody had told me that when I was first trying to learn how to shoot baskets, I probably would have made me worse. Because it's like, you have to be this close.
exactly, why try? You're never going to make it. That's exactly the effect it had on me.
Hey, Doug, have you ever seen a guy on YouTube on Stuff Made Here?
No.
He's a young guy. I can't imagine what he does for a living, but he's really good with the CNC machine, and he actually built a hoop on his wall in his shop where he could shoot a basketball and it would move and he would never miss. So he gets into a little bit of like the arc length that we did, except he has a camera and he had to basically put in a supercomputer all the different possible shots and different arc lengths in his entire wall of his garage there. And the hoop, he went through a bunch of process. I'll send it to you. It's like a little 10-minute video. It's really interesting.
Yeah, I want to watch that. There's all kinds of creative, awesome nutcases out there. That sounds really cool. One of the takeaways I would love to leave you guys with, and it's like, learning math is great. I love math. But overall, I hope you're curious. Like, I hope you have some element of curiosity to you. And I don't mean just math, but it's like, keep learning your whole life. It's fun just to figure out how stuff works, figure out, when you flush your toilet, where does it all go? Or, how does electricity get to your wall and you're like, why does this light bulb work right here? And you know, it's really cool to understand all those things, as well as just, you know, physical challenges like, can you walk on a balance beam, or can you ride a wheelie on a bike, or, you know, things of that nature. I mean, it's fun to like accomplish stuff. And I hope you, to me, that's the larger takeaway from education. It's just fun to understand stuff. You know, in my case, I spent a concentrated couple of days because this problem got in my head, and until I kind of figured it out, and then I was just done with it. And you know, I haven't really thought about it much since then. But it's kind of cool if I go to a game, it increases my enjoyment of the game, just to be, you know, some guy shoots a 3-pointer or whatever, and they make it. It's like, you know, I could turn to the person next to me and say, you know how amazing that is. I'm not going to explain it to you because you would leave me right now if I tried. But cool. Well, all right. So to that end, let's build a formula that I left you with on Thursday, which is the surface area formula for a ball. We'll call it a basketball, since we seem to have basketball stuck on our brain right now. Because all I want to do with the rest of today is just grow your intuition about how surface area works. So what I left you with last time was this problem. And again, I hope you had enough time and or creativity to consider this question. But if I take this chunk of a sphere, remember the equation for a circle is x squared plus y squared equals the radius squared. If I set it at 0, 0, and of course, if I'm going to rotate a ball around something, I'd be nuts to move it somewhere else. Like, I don't want to move it way over to the side and then rotate it around y equals 7 or something like that. I'm going to put it in the simplest place possible. Now, I don't really know right now if I should rotate this around the x-axis, or if I should rotate it around the y. And because of the symmetry of the shape in this case, it actually doesn't make any difference. I'm not really sure. I think I want to go around the y, just because it seems more awkward. Maybe we'll learn something as a result of that. So let's take it around the y-axis. So the concept is, as I said, that we're taking a little slice of this, teeny, so short, just like the basketball problem, that we can consider it to be straight, even though that's actually curved. And I want to spin that thing around the y-axis. And I want to add all of those slices up. Now, in previous sections, we said, let's do this for volume. And so our formula was based on the volume of that little slice. And that slice would be as far as volume, would be a cylinder. But in our case, we're figuring the slice as surface area, because I want to know the distance around it. I want to know the surface area of the basketball. So we're thinking of this as like a piece of paper that's been wrapped around this, not as a solid cylinder. And so all we have to do is just, well, it's the same thing we've been doing, but we just got to add up the areas of that. And so we said, let's see, what is that area? I'm just making it up. I don't remember this, but I'm making it up from scratch. If I stretched it out, it would be 2 pi r in length, the area of my strip of paper, so to speak, that I'm wrapping around this ball. It's 2 pi r in length. And unfortunately, its height is, well, the square root of dx squared plus dy squared, which was our derivative formula. That's its height, which again is really just that length right there. So you can actually reason this out for yourself if you have a good grasp on some of the geometry formulas that you've used in your life, which I think is a tall order. I don't know why you would have that good of a grasp on that. I probably for this next test will make a note sheet for you that has formulas like this on it. Notice this would be the formula for going around the y-axis. If we run around the x-axis, it'd be slightly different. But of course, if we're going to take this around the y-axis, then doesn't the radius of this become an x coordinate? So, for as far as like the formula sheet that I might make for you for the test, I'm not going to put r there. I'm going to put an x there. R would work every time. Like if you spin it around the x-axis, that'd be the same formula. But in this case, I'm spinning it around the y-axis, and so the radius is actually x. So cool. I'm on my way. So I can say then that if I just add all those up, add all those 2 pi x's times the square root of 1 plus the derivative with respect to x squared, I'll just add all of those up while, let's see, we're working with x's. And notice I didn't have to trade anything out, like everything is x's, but what values is x going to take on if my slice works its way from, where I have it all the way to the top and all the way to the bottom? What value for x's will that take on? Well, what is it when it's down here? What's the x value right there? That's not obvious because I'm trying to make the formula for this. I'll let you think about it for a second.
That's the radius, isn't it?
Exactly.
Like, is that what you wanted? Not.
Yeah. Because what I'm trying to do is make a formula. I'm not giving you a particular question. I'm trying to make a formula for surface area that turns into an algebra formula. And so since that r is the radius of the sphere, then that distance right there is r. So the biggest x will ever be is r. What's the smallest it will ever be when it's way up here?
0.
0. It's going to go all the way to 0. It's going to get really tiny. So can you see how that's describing every location that our little slice is going to be in? Now in this case, I'm in great danger because I'm trying to do this algebraically, which means I can't just cheat. Remember a second ago when I wanted to find the arc length of my basketball shot, I looked at the integral that I set up and went, I'm not going to be able to do it. Well, here, because I'm plugging in r, not a number, I can't cheat. Like I can't just type this in my calculator. So I got to think about this a little harder. And then secondly, there's one thing that's missing here that I left off. What am I getting? This is not, what is this the surface area of? It's actually not the whole sphere.
Be half of it.
Yeah, isn't that the top half? So maybe rather than just put a 2 out in front right now, I'll just kind of make a note. This is the top half, and I'll add that 2 later on. So let's go figure out a couple of things. Well, because this is asking for the derivative of y with respect to x, does it make sense I have to solve this for y? So y would be r squared minus x squared square rooted. And I'm going to have to take the derivative of that, right, in order to stick it in there. So y or f of x. Fortunately, derivatives aren't terrible. You can always take a derivative. So let's see, what's the derivative of this? And by the way, I'm looking at this thinking, God, this does not look right. Something looks wrong. This is terrifying. I can't believe we're going to be able to take the integral of this. Maybe I spun it around the wrong axis. Maybe, I don't know. So what is f prime of x or y prime? Well, because this is junk to the 1/2 power, oops, then because of chain rule, I've got to take the derivative of that outer 1/2 first. So chain rule says take the derivative of the outer junk, leaving the inner junk alone. So power rule would say bring the 1/2 down, subtract that exponent by 1/2, and now multiply by the derivative of what's inside. which is negative 2x. So there's the derivative, and I have to square it. This is not good. So let's see what happens. So if I pull that 2 pi out front, and now it's not top half only, I'm going to multiply that by 2. And I just kind of rewrite what I have. Then I still have the x out front, and now I'm about to have this disaster that terrifies me. So this disaster squared. And so let's see, you should be able to do a little bit of algebra in your head. That exponent negative 1/2 would move it to the bottom. So the negative 2x is on top. And the 1/2, that 2 is down there. And then if I move that negative 1/2 to the bottom, isn't it a positive? So isn't that my derivative just written as a fraction? Hopefully your algebra skills can allow you to see what I just wrote. Again, feel free to interrupt. I've told you I want to teach you algebra on the fly too.
Wouldn't the 2's also simplify out?
Exactly. So now I can see the 2's cancel out. And so this has got to be squared, right? And all of a sudden I have a tiny glimmer of hope, because isn't that square going to get rid of the square root? So this seems like way worse than what we just did with the basketball a minute ago, but maybe I'll be able to survive this. I'm not really sure. So yeah, notice I still haven't taken an integral. I'm just trying to simplify this disaster a little bit to see if I can make any progress with it. So if I cancel the 2's and then square the top and the bottom, notice that's a negative x. And so if I square it, it becomes x squared. And then down there on the bottom, so the 2's cancel, the square root of something squared, that just means the square root goes away. Now I still don't think I can do this, but at least it doesn't look as bad as it did before. But again, this illustrates why algebra is a language that you need to be able to speak better than you are able to speak it right now. Because my inclination when I stare at this is to kind of quit and say, well, I can't do that. I mean, there's an x outside, there's square roots of stuff squared, fractions inside like this. I'm not going to be able to do this, is my gut reaction to this. And you had assignment questions with this type of algebra in them. You had and will have. But I'm not going to quit right away. Why am I not going to quit right away? Well, because, I mean, this says add, right? Like, can I add those? Yeah, I mean, I don't know if it's going to do any good, but I certainly can. Notice I still haven't taken an integral because it's too dang complicated. But if I found a common denominator, wouldn't that 1 be r squared minus x squared? So that's what it would take to add them, right? Have a common denominator. What wonderful thing happens though when you add those?
The x squared on the top goes away because it's 1 plus 1 minus.
Exactly. I can now add these and I have a minus x squared and a plus x squared. So I by no means think I'm out of the woods, but it's like, maybe this is going somewhere. So let's see, I just have an r squared. So I still have to take the integral, and I think I'm as far as I can go. I can't think of anything else to do. And again, resist the temptation to go, I'll just cancel those out. You're screwing up the distributive law if you do that. You can't do that. So I can't think of anything else I can do. And although that was really great progress, I'm feeling defeated now. I'm feeling like I still have an X outside. I have stuff pretty ugly inside. Remember that R is a constant. So So, that's not as terrible as it looks. So I'm just staring at the x's thinking I got to take the integral with respect to x. Does anybody see something that might be worth trying?
Well, isn't it 2r squared minus 2x squared on the denominator?
No, because if you have 1/3 plus 1/3, the answer is not 2.
Oh, okay. Never mind.
Thank you for asking.
Could you try u substitution?
Yeah, I'm not inclined to quit. And we don't like fractions and we don't like square roots. And so at least I could try. And I still feel like this is not going to work. I could let u be equal to r squared minus x squared. Remember how we don't like fractions? We don't like fractions that have, I can't divide. I can't take r squared divided by r squared minus x squared. But maybe that would help.
I'd be tempted to say you should let u equal the entire fraction in the square root, not just the denominator.
I love it. Perhaps u is the whole thing. And I do not know, as good as I am at this, I don't know if both of those work, if only one of them works. If they do both work, is one better than the other? I don't know. I think those are both worth trying, though. Would you agree with that? Maybe we'll have time to try both.
I think it would work possibly, because if all of the r's are just numbers, they're gonna not matter as much when you take your derivative of u and you have an x outside. So everything else is just going to be like scaling coefficient numbers.
That's true. And by the way, that fraction with the square root of r squared on the top, couldn't I take the square root of r squared and actually pull the r out front? And then because that's a constant, I could just put it out here with the 4. Then I just have 1 over r squared minus x squared. Yep. I didn't think of that until just now, but that might be a good idea. Maybe that would save me some trouble. I don't know. I'll continue with what I started and just see if it works. But my sense is all of these are going to work. What's really wonderful when you go get the derivative, because remember, now that I've decided I'm going to switch this into u land, why I've got to take a derivative to get rid of that dx. But what wonderful thing happens here that I'm pleasantly surprised about when I take this derivative? So the derivative of r squared is not 2r. R is a constant, so it's 0. What am I really happy to see? That I suddenly, for the first time, feel a great sense of hope that this is actually going to work. Why am I really happy to see that?
You'll be able to cancel out the x's from outside the square root.
Yeah, that x was still a problem out there, and it's now going to cancel. And so for the first time, I'm actually thinking, this might actually work. I can't believe it. Well, let's keep going. So notice I still haven't taken an integral, but I have x times the square root of r squared over u. And by the way, another option would be to say u squared equals r squared minus x squared. Suddenly I'm wondering if that isn't a good idea too. But then to replace dx out there, then wouldn't that be du? If I move this to x over to the other side, isn't that du over negative 2x? And so, yeah, baby. Bam, bam, those are gone. And I'm kind of liking being in the land of u's. And so let's switch this out. If I switch out, because I can't put r in 0 anymore. Does it make sense? That's not true if I say that. I'm probably not going to mark you down on a test if you say that, but that's not true. You can't put in r for u. Like you got to fix those. Because those were x's. And so, well, let's go figure out what they are. Then that'd be r squared minus, well, r squared. Well, that's weird. That turned into 0, didn't it? And then if u is r squared minus x squared, but x is 0, then that's actually r squared down there. Isn't that kind of weird? Like that's what the limits of integration turned into.
And And you don't rearrange those, do you? It just stays as 0 and R
Yeah,
squared.
and by the way, it's important not to rearrange them. You might be tempted to, but if you rearrange them, you're going to get a negative answer, right? So it seems like they're backwards, but what we're going to end up with is a negative answer that turns into a positive as a result of this. So let's clean this up a little bit. When I'm suddenly thinking I'm actually going to be able to take an integral now for the first time. And so let's start getting rid of some stuff. Well, would you agree there's a -2 that I can move out in front? And as I said a minute ago, that r squared, I can actually take the square root of r squared and pull that out front, so that I now just have 1 over the square root of u, or u to the -1/2 power. Wow, I can actually take that integral. I can't believe there was a way out of this mess. That's amazingly cool. So there's been integral signs the whole time because all I've been doing is trying to make the problem simple enough that I can do it. So integral, I've never taken an integral yet. It's just too tough for me. So I keep working on it. Finally, I can actually take an integral. The integral of u to the 1/2. You add 1 to it, so it becomes u to the 1/2. And then you divide by 1/2, which is multiplying it by 2. Now I've actually taken the integral, which then I can evaluate at 0 and at r squared. And from back here, there's I guess that'd be a -2 pi r sitting out in front. You agree with that? See that negative sign out front? The fact that the integral is from 0 to r squared, kind of backwards, that's going to fix that negative sign. Because there's no such thing as a negative surface area. That doesn't even make sense. So of course, when I put 0 in, I get 0. But when I put r squared in, notice something wonderful happens. I get 2 times the square root of r squared, which is actually r. What do you get when you multiply that out?
4 pi r.
Close.
Oh, 4 pi r squared.
4 pi r squared. That is ridiculous. That is ridiculous on a lot of levels. Number one, that's the simplest formula I have ever seen. Like, that's like the area of a circle is pi r squared, and this just says multiply by 4. So like the most basic algebra student can now find the surface area of a sphere. All you have to do is take the radius, square it, and multiply by 4 pi, and you're done. It takes like 1 second to find the surface area of a sphere. Other things that are amazing. Remember, you're covering the sphere with squares. When you say you're all done and you say the answer is, 19 square inches, you're literally laying squares of paper on a sphere. Think about people that make basketballs for a living. You can't make it round, like you have to cut out leather into shapes and kind of fold it around the circle in some way. You have to cover it. The baseballs are really kind of a cool example, by the way, just as a side note. I played a lot of baseball. If you cut out 2 of those, baseball, they wrap around each other and you stitch it together. It's what makes a baseball. Leather's a little bit flexible, unlike paper. And so just remember, we're covering this thing with squares. And secondly, like, you have to be like a math genius to make this formula, right? I mean, this is amazing. You have to know, you have to be really good at all the things we've been talking about lately. You have to be awesome at algebra to pull this off. And yet the end result of all of this ridiculousness, and again, isn't that what you're looking at right there? One of those things you see on CSI TV where there's some nerd who's trying to solve the crime. The other people are out gathering evidence and he's like staring at a chalkboard and drawing figures and so forth. That's what the chalkboard looks like, is some ridiculous bunch of formulas and so forth. And yet this actually did produce something. I mean, it produced something that is really beautiful, really simple. And it's calculus that gave us this formula. I mean, I think that's what you need to understand. So that's on all kinds of formula sheets. Go Google search the surface area of a sphere and you're going to see 4 pi r squared is the answer to that question. But it's thanks to calculus that we have it. So, again, as I've said before, do we need calculus? Part of me says no, we don't, because somebody's already figured out this algebra formula for us. And so if you want to go build a baseball, now you know how much leather you need. That's a very practical formula for some things. Part of me says, yeah, we do need calculus because, like, God, I want to understand that. You know what I mean? Like, this is beautiful. I don't want to miss that. It's like, there's a beautiful waterfall. Well, I want to go see it. Seems kind of a shame to not know stuff. There's stuff to know and you don't know it. So it's part of me says that, everybody needs to know this. Part of me says, yeah, nobody needs this stuff. You don't need this to go build baseballs or whatever. I don't know what to think. But I'll know, not because of my job, but it gives me a quiet satisfaction inside. It's not something that I have to demonstrate to anybody else, but it gives me a quiet satisfaction to know that I can make that formula for myself. That's really powerful. Go back and study that over. It's not something I'm going to ask on a test. I'm going to ask more straightforward questions than that, but I think you can learn a lot by looking at a question of that magnitude. How's your brain? Are you in pain? Are you dying? You try to set this one up. As I said, all I really want to do is practice. Let's rotate. Let's keep this really simple. Let's rotate y equals x cubed around the x axis. And let's just think of it from x equals 1 to 3. And let's find the surface area. Of that shape. Again, notice I'm not rotating I'm not rotating an area. I just gave you a curve. But if we take that curve and we spin it around, we're getting kind of a hollow cup, and you should have a rough idea of what x cubed looks like. It looks something like that. So what we're really doing here then is taking the shape from here to here, and we're sending it around the x-axis. And so we're looking for that surface area. We want to build that. Again, this is a coffee cup. This is a harder version of the coffee cup because it's got kind of a curve to it. In terms of manufacturing, that'd be very difficult to build. And so nobody manufactures cups like that, although it'd be really cool. I think you'd be able to sell them if that was possible to manufacture them in a way that didn't make them 10 times as expensive. People love stuff like that. They love to stand out. So, sell cups that are curved. But somebody's got to know how much paper it takes to build that. There's not a formula for this one. That's the beauty of calculus. You don't need a formula. You need a method. We have a method. Can you set up the integral for that? And by the way, on the test, I'm going to draw these kinds of figures for you because I think not everybody's artistic and can draw something that looks at least vaguely three-dimensional like I just did, but it's really helpful to be able to picture it. Even if you go to Desmos and just draw the curve, that's great, but it's like some people can visualize it spinning around and are really good at spatial awareness. Other people aren't. So it really helps to have a picture of it. So I'm going to draw a picture for every question of this type that you need on the test so that you can kind of sketch on it. Just give you a second to set it up ahead of me. And I just made this up, so I don't know. Are we going to be able to take the integral? Remember, these are pretty hard questions that get made up, so the chances we're going to be able to take the integral of this are pretty small, I'd say. Let's see if you got it set up right. Do you agree that this time the radius is y? So that the surface area equals 2 times pi times radius, which in this case is y. And that length over there, the height is still the square root of 1 plus, I think this time I'll just call it y prime squared. Since I named the original equation y equals x cubed instead of f of x equals x cubed.
Since we're solving the equation in terms of y, shouldn't it be dy and not dx?
Well, remember you have two choices for this. You could say, because you should look at this and go, oh no, that says dx and that's a y. That's not good. Like I can't leave that y alone. I've got to change it to x because of that dx. The other option you have here, you don't have that y is y, but remember the other option you have here is 1 plus x prime dy. In other words, we don't care what you call that arc length. And I showed you that last time. I won't show it to you again, but those are both possible. And of course, I'm a little happier with this one because everything is y in that second. The only downside is I would have to take that equation up there at the top and solve it for this one. I'd have to say that x is equal to the cube root of y, or y to the 1/3. So then I can take its derivative, which would be 1/3 y, and then I subtract 1 from from 1/3. 1 minus 1, 1/3 minus 1 would be negative 2/3, which isn't so awesome. So that'd be the derivative of x. So if I use that second one, then I could just plug that statement I can plug this statement and at least I'd have it all written out, right? So would this top one work? Let's kind of look at both of them. Well, since y is equal to x cubed, then couldn't I just replace the y with x cubed? Now everything is x's. They both are going to work. Let's take a look at what the two integrals would look like. So the top one would be, since I'm working with x's, remember we said x was between 1 and 3, so that's kind of nice to stay with x's because I'm going to write x in here. X equals 1 to 3, so I switch out the y so that it's x's. And of course, the derivative of y is really easy. Isn't the derivative of y 3x squared? That's going to work. And if I'm you and I'm in my open math and I look and it says give the answer accurate to 3 decimal places, I'm going, yeah, I'm cheating from now on. I'm just going to type that in my calculator, get the decimal answer and type it in. I'm assuming that's because my open math knows, or the person that wrote the question knows that this is an impossible integral to take, and so they're just letting you off the hook. Maybe that's a hint. I'm not sure. Oh, by the way, I forgot the squared. That derivative is supposed to be squared, right? I'm going to rewrite just a couple of things here. So I pull the 2y out front. If I actually square what's inside there, doesn't that turn into 9x to the fourth? Does anybody see why this actually might be possible to do? We actually might be able to do this. Why?
You could substitute under that square root.
Yeah, notice there's an x to the fourth under the square root, and I'm not happy with how ugly what's under the square root is, right? I wish that was like the square root of u or something really simple. But if I let u be 1 plus 9x to the fourth, isn't the derivative of that have an x cubed? And so maybe that x cubed would go away. I actually think this is going to be doable. We'll go back and do that in just a second. No, let's actually do it right now. So again, I think this is good practice because substitution is so hard. And by the way, we're going to do substitution harder in chapter 8. So we need to be good at this. So I actually think I might be able to do this. Let u be equal to 1 plus 9x to the fourth. So that du is equal to 36x to the third dx, which means that I'm just going to rewrite it. Dx then would be equal to du over 36 x cubed. Yeah, those x cubes are going to cancel. I might actually be able to do that. And then if u is equal to 1 plus 9x squared, that'd be 1 plus, 9x to the fourth, 9 times 3 to the fourth. Wow, that's a huge number. 3 to the fourth is 81. 1 plus 9 times 3 raised to the fourth. Ooh, can't type. Clear. Plus 9 times 3 raised to the fourth. 730. Wow, that's amazing. And when I put in 1, I end up with 10. So that's incredible. So let's rewrite this thing. So I got a 2 pi out front. It now goes from 730 to 10. And I have an x cubed, but I now just have square root of u. And then dx is replaceable with du over 36x cubed. Bam, those go away. So yeah, I actually am going to be able to answer this exactly right. This is a problem that if I or my open math wanted you to give an exact answer, I guess they could have expected that here. So I can pull the 36 out front. So I have pi over 18. And all I have is the square root of u. Like that's the easy integral to take. Amazing. So I can actually take this. Wouldn't have thought. So I'm finally taking an integral. So now I can say I've taken it. U to the 1/2 becomes u to the 3/2 when I add 1 to it. Notice this time it was positive, not negative. So when I add 1 to it, it's 3/2. Divide by 3/2 would be multiplying by 2/3. Evaluate that at 730. Evaluate that at 10. I'm taking the square root of 730, and that's not a perfect square. So if I type that in, I'm either going to get a decimal or I'm going to get some, really ugly answer to this. In the interest of time, since I see it's 9:20, I'm just gonna stick those in as decimals. So what is 2/3 times 730 raised to the 1.5 power? And by the way, I could pull that 2/3 out in front. 2/3 doesn't have to be inside there. It'd be nice if I did, frankly, but I didn't write it that way, so I'll leave it alone. I got 13,149.009. I'll call it 0.1. And then when I go back and I put 10 in there instead of 730, I get 21.08. So all told, I subtract those two decimals. I say times pi divided by 18. I'm getting that the area is 2291.2.3. And again, I'm going to say square centimeters, even though there was nothing saying centimeters. Doesn't that seem kind of large? 2,000? I'm actually kind of thinking I got it wrong. And I'm not kidding when I say that. 2,000? It's really that big? Well, notice when you put 3 in, notice when you put 3 into that, you do get 27. So that thing is pretty tall. In other words, this is the 0.327, and this is the 0.11. So my drawing wasn't to scale, but I still think I'm wrong. Actually, I don't think I'm wrong, but I just can't get my mind around how that could be so big. I don't see that I made any mistakes. But let's just cheat on this second one since we're out of time. So that bottom one is 2 pi y, which we decided we're going to leave alone, times the square root of 1 plus, and we said x prime was equal to 1/3 y to the negative 2/3, and that is squared dy. What's missing from my integral? And I'm ready to go. Those.
Your limits.
That's exactly right. What are those limits?
One and 27.
Right. I was working with y values, right? So I'm working with y values. So these have to be y values. So that second method was all with y's. And so this is from 27 to 1. Now, again, will I be able to do this if I squared that and worked it all out and made some substitutions? I don't know, but let's just go cheat. Let's go cheat really quick. Just so that this is in the, so remember 2291. So we're just going to see if we cheat and get 2291, but I'm going to go to Desmos to do it. Actually, I can do it on my iPad. I'll just go there. Let's see, to cheat, we said, I think we can just say this. I think we can just say the integral from 1 to 27. Come on, give me a 7. And then it was 2. Come on, man. 2 and then pi. Where's pi? Is that pi? That doesn't look like pi. I'm not sure. I'm just going to type pi because I know it'll switch it for me if I do that. And then it was times y, except for I'm going to switch this to x. And then it was the square root, which I can just start type at xq, sqrt. There it is. And then I'm going to type it. No, there it is. Duh. And then it was 1 plus, help me remember this, 1 plus 1/3. Was it negative 1/3? Was it 1/3? I'll go back and look in a second. And then it was y to the 2/3, negative 2/3 power. Is that right?
Oh, is this, we're doing the dy one?
Yeah, but I just typed. I'm not sure it would work if I used y values, so I'm putting x values in instead.
Yeah, that makes sense.
I don't even remember, was that what it was? Negative 1/3. Positive 1/3. It's not going to matter because I'm squaring it, but it was positive 1/3. I think that 2 that I have out there is squared. So how come it isn't working again? How come it's not telling me?
You need your dx. You need your width.
Exactly. You got to get your dx in there. I like that it doesn't let you get away with that. I just think that's kind of interesting. Oh, got the same exact answer. I can't believe it. That's amazing. I'm not doubting the answer anymore. As I said, I doubted it because it just seemed too large, but I didn't see I made any mistakes. I went kind of slow and I just got the same answer using a kind of a slightly different approach. So now I'm sure it's right. I can't believe y equals x raised to the 3rd. I shouldn't distort that. If I graph the point 3, 27. I wish there was a way to like chop that off and then actually spin it around so we could see it. There is kind of a way to do it in GeoGebra, which I mentioned the other day. I just found that like last night, but that still looks huge. But notice it's up there at 27. And if you think about this thing spinning around in circles, that's a radius of 27. And so that's a pretty big number. Amazing. All right, I've kept you too long, as usual. So get yourself out of here, and or stay after if you want to double check some things or ask any questions. Otherwise, we are doing a application project for this tomorrow. Much easier project tomorrow. Not near as hard. You'll probably get it done during class. It's very hands-on. I think it'll help you do better at what we're talking about right now. It'll help you be better at what we're learning. So it's kind of a chance to practice. And I'll post that today if you want to look at it ahead of time. It's not going to take much explanation from me for you to understand it. So you could think about it ahead of time so your class time is a little more productive if you have time or want to.
Doug, I have a question about 6.6.
Excellent.
So in the My Open Math question number 2, I'm having trouble with that one.
Okay, I am sharing my screen and going to find that. Yes, go ahead.
Okay, so I did the problem a couple of times and I keep getting it wrong. And I'm not sure what I'm doing wrong.
So you sent it around the x-axis. And it's this y equals 5. And is yours is a similar problem? It's a line, right? But it's probably not 5x plus 1, something like that.
Yeah.
From x is 2 to x is 5. Okay. Let's I'm going to just get a clean piece of paper. Let's kind of work your problem and so what is yours?
Y equals 4x plus 5. And then the the range is 2 to 5.
So 4x plus 5 kind of crosses up here, and it's really steep, but I'll draw it flatter than that just so it doesn't go crazy. And then they said go around the x-axis. So do you agree that from 2 to 5, you're talking about that, and that spins around this axis? So it looks something like that. Do you agree with that? So tell us what you did.
I did 2 pi y and then the square root of 1 plus 4 squared dx.
Do you all agree with what she said? What April said? So the slice that you're taking through this time I'll draw this slice as just two-dimensional. So she's right. That's y. 2 times pi times y. And then 1 plus the derivative. The derivative of 4x plus 5 is 4. I don't see a problem with that. And then you evaluated it from what to what?
From 2 to 5.
Cool. So what'd you do with this?
I put in 4x plus 5 for y.
Good job. I haven't heard anything wrong so far.
Okay.
Would you agree that under the square root, thankfully, is just a constant? So what did you do next?
Did you write 17?
Yep.
I have 9.
Plus 4 squared is?
Oh, that's what I got wrong.
What'd you do wrong? Tell us.
I did 4 plus 4 instead of 4 squared.
Got it.
Okay, thank you.
Do that kind of stuff all the time. All the important stuff you totally had right. I love it. Keep going. Who else has questions of any kind?
I have a question about the quiz.
Sure.
So for problem 3B, I wasn't quite sure what you meant by saying find the total distance the ball travels, because you could see that kind of 3 different ways. You could see it as the total distance is the equation, or is 0 because it didn't travel any vertical height. But I'm assuming what you meant is to find like the length of the graph, I suppose. So would the answer to that question be 514.813?
That is correct.
Okay, I was just making sure.
Yeah, and you make a good point from technicality. Yeah, I just meant kind of like the arc length of the basketball.
Yeah, you mean baseball? I'm pretty sure it's a baseball.
Yeah.
No, yeah, baseball.
I was referring to the arc length of the basketball project we started the class with, but you're right.
Oh, yeah.
Say that total distance it travels, you know, is that like X? Is it Y? Is it a net distance because it started at 8 feet and it made it up to 10, so it's only 2. So yeah, I meant that in its sort of least complicated way.
Yeah, my second question is for problem 4. I just wanted to check my answers. Is the correct answer for that 125.723?
Yes.
About? All right, cool. Thank you. I'll see you tomorrow.
See you tomorrow. Keep going. What else?
I had a question about that extra credit bead calculation that you mentioned.
Yep.
So I think I have it worked out in Desmos with a big R and a little r, but I just want to make sure, because I'm getting a negative volume instead of a positive volume, and I'm not sure what I've subtracted wrong. So do you want me to show my Desmos?
Yeah. You have the power.
Okay. So this is what I ended up with, and this is, I think it's basically the same volume as I got on my project, because based off of these dimensions, but it's negative.
Let's see, can you retrace, because I'm staring at mine and you have it all right. Can you retrace why there's a negative in front of that 2 pi?
I don't have my scratch paper handy. I'm gonna guess it's one that I factored out.
There's a couple of reasons, because it could be like from the very start, a lot of people on that project subtracted like you should be taking the outer shape, which is like the largest radius, and subtracting from it the smallest radius. In other words, the outer radius of the bead minus the radius of the cylinder hole. And if you got that backwards, that would cause it to be negative without being wrong.
Yeah.
That's a possibility.
I'm trying to remember if I got it backwards in my project too.
Yeah, I can't remember if I pointed that out to people. There was a lot of people that did that, like that conceptually. In one sense, it's not a big deal, but it does make the answer come out negative.
Okay, I can go through it again to see what I missed, but it's good to know that I got it. At least it looks right.
Correct, yeah. Basically, put that negative away. That's the formula. I would say it's a little, since you have 2/3 in there, as far as, what, if you were saying, hey, I'm going to give you this algebra formula that you can use for the rest of your life, Mr. Bead Nerd. It would be nice to take the 2/3 out and call that 4/3 pi out front. Does that make sense? Kind of like the volume of a cylinder is 4/3 pi r cubed. I mean, that's
Yeah.
where that is. So just get all the constants together. But yeah, everything else is gorgeous. So.
Okay. Also, so for the project, we ended up with a margin of, with a phi of 0.470, 0.468. And I noticed that when I subtracted that, when I did our 64-degree initial angle minus that and plugged it into Desmos and then graphed it, the ball would it appeared to hit like at the center of the ball. It would be kind of on the front of the rim.
It hit the rim a little bit?
Yeah, so I wondered, like, at that point, is that your margin of error? Because at that point, if you hit at the center of the ball on the front of the rim, does it like have chance of bouncing in or out of the hoop?
Yeah, basically, if it hits the rim, it's kind of like a flip of the coin as to whether you'll get lucky and it'll still go in. If it just barely grazes it, that's still fine. But at some point, it hits it hard enough that it bounces away. My guess, though, in your case is, there's a lot of rounding involved in this.
Yeah.
Unless you're like my A value just a minute ago, I carried out to 4 places. That's not enough. Like if you want it to actually really look good at the rim, you got to have the whole thing. So my guess is you're awesome, because the right answer to these is about 1/2 a degree. That's about the error you have, is from a third to 2/3 of a degree is all the error you have, depending on what angle and length you chose and all that. So the fact that you got that angle, I think you're right.
Okay.
So I'm almost 100% sure it's just rounding that made it hit the rim there, because you're right. It should have just grazed it. You should have saw it just, just barely touch it, if you had that correct.
Okay. That was all. So I'll see you tomorrow.
Yeah, by the way, one thing to double check that is, does your ball actually go through the center of the rim? Because it probably doesn't, depending on what you typed in for A. Unless A was perfect, it won't be, the actual angle you chose won't be going through the center of the rim either. You see what I mean?
Yeah,
That's kind of a way
yeah,
to,
there were definitely
yeah, it's just,
slightly crooked points. And I think we, in the document we submitted, we included a link to the Desmos graph that we were working with. So
yeah, fun.
yeah.
Sounds like you nailed it. Good job.
All right. See you tomorrow.
Yeah. Other questions?
I have a question and a comment.
Okay.
It's good to know that the error was supposed to be between like 1/3 and 2/3 because I think I got mine at 0.66. So I think I might have maximized my shot by accident.
I think you might have. What angle did you pick?
60 degrees, I believe it was. And I used like my height, which is like I'm around 5 foot. So I think I did 6 foot
Mhm.
throw because your arms are up. So I just kind of based it off of like my height.
Good for you.
And then my other question is, do you normally post the like just like after class discussion also on YouTube or no?
It depends. Like today, I didn't stop the recording. Some days I'll stop the recording once the class is over, and today I didn't, so it'll be there today.
Okay.
I would say by generally speaking, I would say yes, only because I'm trying to keep it from being ridiculously long. Although, a lot of times people ask pretty good questions, and sometimes people hang around even not having questions, but just because they want to hear other people's questions, and you end up learning something as a
I
result.
do that a lot. And then sometimes I'll remember like, oh, we talked about this issue after class with a problem. And then I'll be having the same issue and I'll try to go back and I'm like, oh no, it's not there. I did that yesterday when I was looking back at the project because I was getting stuck on the like getting all of the stuff for the degree of tolerance right.
Yeah.
But it wasn't posted on the lesson and I was like, oh no.
Yeah. I'll actually keep it running for me in here.
So
Anybody was really looking at it, so I'll save it. Good thought.
that is all I had to add there.
Thank you. Anybody else? All right. I will see you all tomorrow. Have a good day.